There they are, the calculus students. Well, the 5 of you that are on time. Good morning.
Good morning.
Morning.
All right, we're going to blow our minds a little bit today. Is that a normal weekend? Feels like it was forever. I'm sharing a screen and we're going to get after it. So today we are looking at lines and planes. We're looking at kind of our first round of equations that exist in 3D. This is a topic that really begins here and ultimately comes to its sort of full fruition in Calc 4 that I hope you're taking this summer. I sent you guys an email about that. If you haven't signed up, you should. ASAP, just because we may have to cancel the class if we don't get to a certain size. But
Oh no, that would suck.
But I do make a pretty good argument to the school that we need to keep it just because it is part of a sequence. So we'll certainly work hard on that. Let's see. How did I lose my share? Resume share. I don't know what you guys see right now, but it sure looks like my share went away. Do it again. So 13.5, the last of chapter 13. I did kind of accidentally lie to you guys the other day. We aren't having a final exam in this class, which I know is very disappointing to you. And we're doing 13 and 14 combined. So we're basically spending today on 13.5, the last section in chapter 13, and then we're going to move on to 14. I don't know if we'll get done today. I really don't want to rush through today. I want to give you a chance to really understand this if possible. So I want to leave time to kind of play around. Let's see. Seems like it's behaving badly today. Check my internet connection. Dang it. Don't see anything wrong there. So what I want you to think about is what would the equation of a line look like if the line was not in 2 dimensions as you're used to, but in 3? That's the question. Let's see, 13.5, lines and planes in 3D. Can I ask what you guys see right now? What I think you see is just
Black screen.
just a black screen. Looks like what I'm writing is just showing up, but way behind. Do you see lines and planes in 3D now? Do you actually see a note sheet?
No, still a black screen.
A black screen. Where the heck is that? Now what do you see?
Your 3.5 lines and planes in 3D.
Thank you. Okay, I don't know why, but whatever. And your intuition on this might be, let's say number one, what would a line in 3 dimensions look like? You can appreciate there's a line in 3 dimensions. And so, my thought on this would be, well, we'll just kind of take it up a notch. In other words, isn't this a line in 2D? Like if I said 2x plus 3y equals 12 or something like that, like that's a line, right, in 2 dimensions. So it seems like, well, I'll just add a 3rd dimension like that. So, doesn't that seem like that would be a line? And I apologize, this is lagging behind because I wrote 4z there about 5 seconds ago, and it still just shows a plus sign. What is causing this? Let me see, maybe it's my iPad. If you have GeoGebra up, you might, that's the problem. Stupid iPad is on the wrong network. I'm guessing this is going to get better now. You might try this yourself, but I'm going to go try it in GeoGebra myself. I'm in GeoGebra now, but as far as I can tell, you still see the same thing you saw before.
Yeah.
What's going on here? So if you have GeoGebra, stick it in there and see what happens for you. I'm going to try, now that I switched my iPad to the right network, I'm going to try sharing my screen one more time. Maybe it will do better now that I'm on the right network. I don't know. Yeah, it's a little better.
Yeah, it looks like it made a plane.
Yeah, oddly, this probably won't be the same exact example, because I'm not going to go back and find it. But if you just add 1 dimension to it, like, plus 4z or something like that, you might think, well, that'd be a line in 3D, but actually it isn't a line. I guess I just want you to cogitate on that for a little bit. I think I'll make this equal to 24. Notice it actually makes a plane, not a line. And so that's kind of weird. And again, it's sort of hard to see. It's sort of hard to spin that in a place you can see it. So a couple of things should happen. One is you should think, well, gosh, that's like the simplest equation you can make, right? I mean, there's no squareds in it. There's no sine. There's no cosine. I mean, you would even probably say that's linear, right? Like it's just because it only has y's and x's and z's, it's linear. And so, man, how do you get simpler than that? If there's a line, how are you going to find a line in 3D? So it turns out that's a plane. Now, part of me in hindsight, if you will, thinks, well, I guess that does make sense. Because if you think about what a line is in 2D, like in 2 dimensions, if you make up this equation and there's no z in it, like 3x plus 2y equals 24, you get a line, which is actually 1 dimension below. In other words, a line is 1 dimensional. So you have a 2-dimensional graph, but you get an equation that's 1 dimension below that. Well, isn't that what actually just happened here? You have 3 dimensions to work with. And then because you put in x, y, z, you got something that's 1 dimension below that, which is a 2-dimensional surface. So that plane's, kind of at an angle, but that's actually a 2-dimensional surface. So in a sense, the larger pattern of this turns out to be that you're just a dimension below. So this is a 3-dimensional graph, but because it's linear, and it really is linear, you're getting something 1 dimension below that. So you're getting a 2-dimensional graph. And so I guess it stands to reason if I threw even another letter in there, like a W, we wouldn't be able to graph it. But if we had a 4-dimensional graph and you graphed 3x plus 2y plus 4z plus 8w equals 24, I guess you would get something that was, well, a dimension below that. like a three-dimensional graph, if you will. So interestingly, the pattern actually is correct. It just is kind of surprising, but you should think, well, man, how am I supposed to find the equation of a line then? If this is the equation of a plane, then how do I get it any simpler? So you might think, well, that's just because you had too many dimensions. Is that a line? Notice it's not. It's still a plane. Now it's parallel to Z, you might notice. It's parallel to Z, and that's probably not a coincidence that having 0Z, it's parallel to Z. I bet if I went in there and left out Y, it'd be parallel to Y based on what I'm seeing right here. But notice taking that out still doesn't make a line. And keep in mind what a plane is actually infinitely many lines. So how do I make it any simpler? Does that make sense? Is that bugging you? Like, are you feeling the tension here? How am I supposed to, I mean, it makes sense there would be a line in 3 dimensions, but how am I going to find its equation? I don't even know what to take away anymore. What if you just keep taking stuff away? Let's take the Y away. What do you think is going to happen now? Oops, wrong button. Bink, 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 bink. What do you think is going to happen? Still a plane. So now you should be thinking, well, it's impossible to make the equation of a line, because what am I going to do? Take the X away, 3 equals 24, take the 3 away. Notice where it hits the X axis. You shouldn't be surprised where it hits the X axis. If 3X equals 24, that means X has got to be 8 every time. X is always 8. And what do Y and Z, what values do Y and Z take? You notice because they're not there doesn't mean they don't take values, just like they did for a line. If I said X equals 6 on 2 dimensions, you didn't just get a dot, you got a line still. And so while X is busy always being 8, basically Y and Z are every other possibility in the world. They're just not, it's not written down, so there's no limitation on them. So the point, X is 8, Y is 2, Z is 7. There's a point. X is 8, Y is 3, Z is -9. And so you might be able to visualize, yeah, that actually is going to make a plane. And so you should be a little despondent about coming up with an equation of a line at this point, because it turns out it's hard to make anything else. So this is actually a plane. So what about a line in 3D? Well, it turns out there kind of isn't an easy way. It turns out you actually have to jump to something that's parametric. So let's just kind of make up 2 points. So 2 points, I'll call them A, we'll make that 3, 2, 6, and B, we'll make that 4, 1, 3. It turns out this is the only way that you can do it. And we'll graph it in GeoGebra to see that. But you almost have to, I don't know, trick it. You have to define it as a bunch of points. That's the way our equations always worked, if you think about it. But let's just think about the vector from A to B. Do you remember how to find that? What do you have to do to get the vector from A to B? Somebody blurted out.
You said do B minus A?
Yeah, you got to go from head to tail and subtract. So you got to go B minus A. So 4 minus 3 is 1. 1 minus 2 is -1. 3 minus 6 is -3. And you sort of have to define the points then, because that's what an equation is just a definition or a limitation on what points work in the equation. So now that you have that, then you could say this. I will start from A, which is 3, 2, 6. And then I'm going to go toward AB, but I will throw in this parameter, which we often use as t. In this case, I don't think time makes a lot of sense. It turns out that's actually the equation of the line through AB. So this is equal to, in the language of geometry, line AB. That's its equation. So 3, 2, 6 gives you kind of a starting point. And then the 1, -1, -3 just tells you what direction to go from there. And then the t says multiply it by anything you want. So in other words, you can make it short, you can make it long, anything that you want. Now, isn't that kind of weird? Like you actually can't graph a line with just kind of x's, y's, and z's. Well, you kind of can. Here's another way to say it. You can say, what's your x value? It would be 3 plus t. In other words, this is x. And isn't that x there as well? So it's 3 plus 1t. That's your x coordinate. Pick any t you want to, and that'll be your x coordinate. And then your y coordinate, which is a 2 and a -1. So then you say 2 minus -1 times t, or 2 minus t. And then your z coordinate would be 6 minus 3t, since this is z over here and this is z over there. So you could also write it like this, 6 minus 3t. So if I just graph a whole bunch of points, pick t to be anything you want, 0. Notice if you pick 0, you get the point 3, 2, 6. Yeah, that was on the line. That makes sense. That point would be there. If you pick t as 1, then you get 4, 1, 3, which is the other point we found. And then if you pick t as 2 and t is 3 and t is 4 and t is 5, basically you're going to get a bunch of points that, well, they all line up. So I am going to snap a picture of that, so forget it. Let's just go graph that. There, turns out there just isn't any other way. So if I shut that down for a second and I just go in here and throw in the coordinates that we just mentioned and say 3 plus t. I guess I don't have any choice but to go over here to get that 3 plus t. I think I can type it in this way. I think there's more than one way you can type it. And then 2 minus t. To take away letters t. And finally 6 minus 3t. Close that parenthesis off. So notice, oh yeah, I guess we finally have a line. Isn't that weird? Like, doesn't it feel contrived or strange, or like something's wrong? Also, did you notice what it typed? Did you notice what GeoGebra did with what I typed in there? It's almost like it said, I don't like it that way. And notice they kind of used lambda. Like I put t in there and it's kind of, it went, nah, not going to let you do that. I mean, it's just some letter, but it basically typed in kind of the vector version of what I said. That's interesting. I shouldn't have expected to do that. I won't take the time to graph it. I kind of want to, but yeah, I probably should, I guess. So let's graph the point 3, 2, 6, 3, comma 2. It's pretty fast, comma 2, comma 6. So cool, A is on there. And then we said B was, I forgot what we said B was. 4, 2, something or other. 4, 1, 3. I just kind of want to see it be on there. Notice I'm not typing, I'm not saying I want this to be capital A, capital B, but because that's the next one in the alphabet, since I didn't name it, it says, well, you're going to have to, I'll name it for you. And it chooses the next letter in the alphabet. So notice it does seem to be working. Can you at least appreciate that that works, even though I guess I hope it still bothers you a little bit? I mean, that is a line. It just feels like it should have x's and y's. But as I said before, if 3x equals 24, which I can't think of a simpler equation, produces a plane, then I don't know what I would do to have x's, y's, and z's in it to get a line. So it's kind of like it had to be simpler, if you will, even simpler than that. So lines are pretty strange in this land. So for the sake of the notes and just so I have something written down, I think I'll throw that in there really quick. And now I want to move on and let's play around with this concept of a plane a little bit more. And we're going to spend the rest of our time today kind of looking at that concept and how do you, I mean, back when you were learning about lines, the thing you did then was you were asked to graph lines that were, parallel. Find a line that's parallel to some other line. That's the kind of questions you were asked. Or can you find the equation of a line that goes through 2 points? And now we're going to kind of try to do that same thing in 3 dimensions. Like, can you find the equation of a plane that goes through 3 points, things of that nature? So you have the basics on how a line works, the fact that there's really 2 ways to say it. Either of these are okay. Both okay. Both versions of the same line. But the thing that I maybe isn't quite so obvious is you can't just, I can't just go back up here to the top and say it's a plus t times 413. Like that wouldn't have worked because that's not sending it in the correct direction. So the vector part of this is you got to send it in the right direction. So you need a vector that goes through those 2 points to know what direction to send it in. So you got to invent that yourself. But let's go back and play around a little bit with the equation of actually, let's graph this first. Let's see if we could graph that plane that I described earlier when we said, I wonder what this thing is up here. I wonder if you could graph this yourself in 3D. Of course, I can cheat, but let's start off with that. Graph of a plane. How am I going to graph this? Well, how many legs does, maybe that's not a good question because some of you, how many points does it take to define a plane? How many points would I have to have? Think of it as like a flat surface, like a tabletop. How many legs is it ideal for this table to have? I mean, if I have just 2, it's being supported by 2 fingers right now. Notice it can still tip on those 2 fingers. Now, of course, I could, glue it to them and it wouldn't tip, but it still wants to tip. Whereas if I put a 3rd finger up there now, like it takes 3 points to define a plane. Does that make sense? So the question is, can you find 3 easy points from this equation? Again, I say easy. Is it okay to pick x is 7, y is 19, and then go solve for z to find a point? Absolutely. But what do you want to do if you want your life to be easy? What's the easiest points you could possibly find?
0.
Yeah, put a bunch of zeros in there. Like for instance, if I put in x is 6, meaning 2 times 6 is already 12, then I'd be free to let y and z be 0. Like there's a super easy point. And notice I made this up to be nice. If I did the same thing with y, 3 times 4 is 12, then I could go back and let x be 0 and z be 0. And if I did the same thing with z, 4 times 3 is 12, then I could go back and let x and y be 0. So isn't that the easiest points you could possibly pick? And again, you're happy I picked 12 here now, right? So that all of those go evenly into 12. And so could you graph that? Let's just take a second and make at least a rough looking graph of this thing. I think I at least need to label what I'm calling x and y when I do this. I notice I made it nice. So x is 6. 1, 2, 3, 4, 5, 6. Y is 4. 1, 2, 3, 4. And z is 3. 1, 2, 3. Now the hard part comes. Are you decent at this kind of a thing? Can you shade? I mean, a plane goes forever in every direction, so it's kind of hard to do this. I mean, the only sort of simple thing I could do is maybe connect all of these points and then don't know, just kind of say, oh, it keeps going from there. And that defines that plane. So it's not that surprising, you know, where this thing is actually going to hit, if you think about it. So you can actually graph a plane relatively easily. And if you think about it, isn't that like what you did with X's and Y's? If you were told 2x plus 3y equals 12 back in line world, you could say, I'll use the slope intercept. I'm going to, you know, solve for y, and then I can tell what the slope is in the y-intercept. But isn't it easier just to say, well, the 0.60 on the x-axis and the 0.04 on the y-axis, it only takes 2 points to define a line. So isn't that faster? I'll just find those 2 points. And because I know that 2x plus 3y equals 12 is linear, meaning it's a line, then if I find 2 points, it takes 2 points to define a line, then I'll just draw a line through them. Well, isn't that what I just did? I mean, this by extension takes 3 points to define a plane. I just found 3 easy points and drew a plane through them. So that's kind of cool. It's just faster. Let me ask you a question. If I start messing with these two numbers over here, if I start messing with those two numbers, the 2 and the 3, how does that line change? What does that change about the line if I start messing with 2 and 3? What does the line do?
Changes the slope.
It's going to mess with the slope, isn't it? What if I mess with the 12? What is the 12 going to do? What if I change that to 14, 18, 16?
It'll just amplify everything to bigger, right?
Yeah. So that's what I want to play with right now, except for I'm not going to go bother to draw the line. I'm going to go back and do this with a plane. So the good thing about GeoGebra, like Desmos, is I can actually just make up letters for this stuff. Let's see. I think I can just go start typing this. Let's find out. So I'm going to type not 2x, but ax. I think because I said a, it's going to go, I can't, a is not a number. I can't do that. So I think it's going to make up a value for me for a and say a is 2, and then I can slide it around. But I'm actually not sure. So let's find out. So if I say a plus b times y, it's b times y plus c times z. And I could say equals 5 or something like that, but I'm just going to say equals, well, let's keep going, d. Okay, good. So it did read my mind and say, I have no idea what you are doing. So the first thing I'm going to do with this is, notice right now it made them all 1. So that's fine. But I'd like you to notice what happens if I mess with d. Can you tell what's happening if I'm messing with d? Do you notice it's not changing? Well, I guess you could say the slope of the plane is just kind of moving it. Whereas what happens if I change c? Why did you do that? I just want to slide you. Why are you making me type numbers? Fine, we'll just turn you on. Whereas notice if I change c, it's actually changing the slope of it. Notice it's also kind of changing the y-intercept, but it's definitely changing the slope. If I let them all change, I think, let's see if it lets them change all simultaneously. Notice you can't, in a sense, can't tell, but A, B, and C, just like the 2 and the 3 for the line, are changing the slope. Whereas if I animate D, it's interesting, it sort of didn't let me make a slider for D. Not sure why. Anyway, you see the idea. So it turns out really that this part of it effectively, I guess you could say, pertains to the slope. Or perhaps maybe you want to use the word orientation. Slope is probably better than orientation. But the key is really 12 is just the position, not the slope. It doesn't change the angle. Things just going to sort of appear to slide up and down. And effectively, that's the same thing that happened for a line. When you mess with the 2 and the 3 over here, you're going to get a slope difference. If you mess with 12, the thing's just going to kind of move up and down. All right. You have maybe just the basics. But now I'd like to show you something kind of surprising. As I said before, some people when kind of playing with a line would say, oh, I can tell you what the slope is of that line. So you would say, okay, I'll take this thing and I will solve it for y. So I'll subtract 2x over, and then I'll divide by 3. And so does it make sense that then you would say, oh, cool, I know some things a little more particularly about this. I know some cool things thanks to putting it in that form. Notice I know the y-intercept is 4. And again, I hope you don't have that memorized. It's really just if you let x be 0, doesn't that make y 4? You have no choice, right? If x is 0, then the negative 2/3 has no input, and then y is left to be 4. So 0, 4 is the y-intercept. And then kind of by memorization, I mean, since it was just your good fortune as a math student earlier in your life to notice if you put it in that form that negative 2/3 happens to be the slope. Can you appreciate that was actually essential? Like we almost couldn't do anything. Remember back when you had 2 points and you were asked to find the equation of a line through 2 points, and then you said, okay, how am I going to do that? Well, if I go y minus y over x minus x, I'll get the slope. And if I have the slope, then I can plug it in right here. Like, isn't that kind of our method for that? But it's like, what if you didn't have that? What would you do? So that's kind of interesting. So let's just stare at one other small thing. So let's see if I made a rough graph of this. Maybe I should even do better than a rough graph, just so that you really see this. I can't remember which one is paper. So let's kind of go down here and graph this dude. So you would say, the y-intercept is 4, slope is 2/3, which is a rise of negative 2, a run of 3. So you'd say this is the equation of the line, I do believe, is what you would say. But again, where I'm going with this, of course, is how are we going to do this in 3D? Like, what if I start asking you the same creative types of questions? Like I say, hey, if I give you 2 points, could you find the equation of the line? If I give you a slope and a point, could you find the equation of the line? We're going to do the equivalent with planes here in just a second. And so I got to show you kind of an amazing discovery. So this is the equation. But I'd like you to take a look at something here that is just a remarkable discovery, if you will, or a remarkable observation. I want you to think about the 2, 3 there. Do you agree that the 2, 3 there is where the slope came from? The 2 and the 3 is where the slope came from, right? In our case, we subtracted 2x over, so that took the sign and made it negative, and then we divided by 3. So if you graph the vector 3, if you graph the vector just like it looks, so consider the vector 2, 3. In other words, I just stole it right out of here, just like it is, 2, 3. How's that going to look relative to the line if I just graph the vector 2, 3? And notice we don't know where to put it. Put it any place I want. How's it going to be related to the line? I mean, the slope came from the 2 and the 3, right? So doesn't it seem like there'd be some related slope? Well, and again, it doesn't matter where I start from. I'm just going to start from, well, right here. If I go right 2 and up 3, would you agree that's the vector right there? What do you notice about those? Is that a coincidence? Well,
It's the same segment as between the 2 points.
yeah, notice the kind of the distance between these 2 points right here was 2, 3. And our distance was also 2, 3. And as a result of just taking literally the 2 and the 3 and graphing them as a vector, it quite, maybe surprisingly, but actually when you stop and think about it a little more, it's actually not surprising that that's perpendicular. Do you understand that? In other words, 2, 3 is what produced the slope. And the fact that we ended up subtracting it to the other side, that's what changed the sign of it. And then notice in the case of the 2, 3, I went x is 2 and y is 3. But in the case of the slope, I went y is 2 and x is 3, right? And so it's not, I mean, that is what perpendicular means. And so the fact that the 2 and the 3 are sitting there, they're actually perpendicular to the slope of that thing. Well, that's what's amazing, is it turns out that fact actually continues. So let me show you something. Let's go graph 2, 3, 4, 12 over here in GeoGebra. 2, 3, 4, 12. 2x plus, that's not plus 3y plus 4z equals 12. And so we get that. And again, let's just stop to notice something. Where does it hit the y-axis right there? Notice it hits at y is 4. Are you surprised that it hits at y is 4? Are you surprised that it hits at x is 3? I'm sorry, x is 6. Are you surprised that it hits at x is 6? Notice it's 2x equals 12. X, it would have to hit at x is 6. If you think about z, 4 times 3 is 12. That means it has to hit at 3. By the way, can you see it hitting at 3 right now? Even though it doesn't show, can you see that? Do you see how the line goes from solid where you see it to behind the plane where you don't? It turns into something dotted. Can you see that that's actually the case? If I zoom in, notice it really does hit at 3. So again, that graph is not that surprising to us, right? But now what I'd like to do is graph the vector, well, 2, 3, 4. So we said earlier, if I recall, that we got to give vectors lowercase names. So if I give it a lowercase name, it knows it's a vector, we said. And so I don't have to put brackets. I would have to if I wrote it down, but I can actually just type 2, 3, 4 in parentheses, 2, 3, 4. And it knows that's a vector. What do you notice about that vector relative to the plane?
90 degrees.
Yeah, it's 90 degrees. Well, that's actually pretty amazing. And so if you want to know the equation of a plane, let's start working backwards now. If you want to know the equation of a plane, does it make sense that it'd be incredibly cool to know what it's perpendicular to? If you knew the vector it was perpendicular to, does it make sense you know almost the entire equation of the plane? So to find the equation of a plane, if I start giving you creative questions, you need to know ultimately the perpendicular, because it's that allows you to write down the 2x plus 3y plus 4z. That's kind of cool. So this is the backbone of everything we're going to do. So log that away in your brain while I make a quick note of it. And I could do something a little more proofy for this. And if you want me to outside of class, I certainly will, because I can, but so this is vector v, and it's perpendicular. That's kind of cool. The other thing I'd like you to stop and think about for a second is this. This is rather kind of an amazing little observation too. Would you agree that if I took the vector 2, 3, 4, and I dotted it with the vector x, y, z. I want you to think about what that equals. What's a dot product? What do you do with those? Don't you multiply x's together and y's together and z's together and add them up? Well, isn't that exactly what this says right over here? And if this is equal to 0, what does that tell us about the angle between those?
Is equal to 0, does that mean it's going straight to the origin?
Yes. What else does it tell you? So if it, no, and notice ours isn't, right? It's not equal to 0, it's equal to 12. But if it was equal to 0, what does that tell us about the angle? Remember back in 2 dimensions when we found the dot product between a couple of vectors? And we had this little formula. When was that angle equal to 90 degrees? What's the cosine of 90 degrees?
0.
0. So if the dot product, the numerator of that fraction is what's going to cause the 0, right? So if the dot product is equal to 0, then they're at 90 degrees. So if this was equal to 0, wouldn't this be hence perpendicular or 90 degrees? Now ours isn't equal to 0, right? However, what if I change that 12 to 0 from the discovery we just did a second ago? If I change that 12 to 0, what would happen to that plane? What changes about it?
It'll just be moved along the y-axis to 0, but the slope should be the same.
That's exactly right. Does it make sense? The slope isn't going to change. It would just take this. It's just going to take that plane and slide it down here because it is still, it's going to go through 0, but it's still perpendicular. Does that make sense? And so, and all I'm saying is it's not actually that surprising that this is the case. It's not that surprising that the 2, 3, 4 is actually perpendicular. So the fact that it isn't equal to 0, but it's equal to 12, definitely that's going to move the plane somewhere else, but it's not going to change the angle of the plane, which means it's still perpendicular. If it's equal to 0, it's going to move it there. If it's equal to 12, it's going to move it where we had it. So this is the backbone of kind of the business of finding an equation of a plane and so forth. So you don't have an assignment question like this, but let's just try to do something here. As an example then, let's say you have the points A, and I'm just making these up randomly, which is a very dangerous thing to do. B, -1, 2, 4. And C, it's called 4, 1, say 5. Would you agree that there is a plane that goes through those 3 points? And notice I didn't make them nice. I could have made them like 5, 0, 0, 0, 0, 9. I could have made it a little bit nicer, but those are just 3 random points. And we did this in line world, right? I said, hey, here's a couple of ordered pairs, 6, 2 and 5, 9. Can you find the equation of the line? And then you went to this really weird system where you went y minus y over x minus x, and that's equal to the slope. And I plug it in over here, and then I find the y-intercept. And so you have this kind of little system that's really weird and awkward to go through. Well, this is kind of the same. In other words, if you want the equation of this plane, does it make sense? What you really need is a vector perpendicular to it. And that's what would be really helpful. Do you see the concept here? Man, if I could just find some equation perpendicular, some line, some vector perpendicular to whatever that plane is, man, I'd be on my way. You agree with that?
Yeah.
So what I really need to find is a perpendicular vector. Isn't that weird that you'd be looking for that? I mean, it's like, it just doesn't make any sense. So if you have any question that says find the equation of a plane, I don't care what's given. I don't care what you're told. Elephants are gray. I don't care what you're told. You're looking for a perpendicular vector to that. Like that's what you're doing. I mean, which as I said, that's what you that's actually what you did here. When you did this with a line, that's the same thing. In other words, the 2 and the 3 there determine the slope, right? If I gave you 2 points, didn't you get busy trying to find the slope? Well, the 2, 3 already tells you the slope. So this isn't as weird as it seems. You went slope hunting immediately as soon as somebody said find the equation of a line. Well, that's what we're doing here too. We're going slope hunting. It's just that perpendicular vector is code for going slope hunting. And it's a nicer way to write it. So this is actually easier than what you did for a line. Now, here's where the trick comes in. How am I going to find something perpendicular to that? Well, let's go find a couple of vectors. So for instance, let's go find vector AB. And we said just a minute ago that you subtract those. And so if I go -1 minus 2, that's -3. If I go 2 minus 3, that's -1. If I go 4 minus 6, that's -2. Notice they all came out negative. And so I'm wishing to myself, I wish I'd went from B to A, because then they'd all be positive. And then let's go find vector C to B. I mean, it doesn't make any difference which one I pick, but I'm just finding a couple of vectors. So from C to B, so I got to go B minus C, -1 minus 4. Looks like I'm blowing it again, -5. 2 minus 1, I finally got a positive number. 4 minus 5, -1. Do you agree that these vectors are on our plane, just like the points were on our plane? Do you agree that those vectors are also on our plane somewhere? And keep in mind, you're kind of picturing the plane like a triangle right now, probably. But remember, they're just somewhere on it. I mean, if I think of a piece of paper and I lay this pencil on it, so there's an arrow on the end of the pen up here and it's pointing there. It's like, does it make sense? As long as it's laying flat here, it can be kind of any place I want, rotated, who cares? It can be anywhere. It's not like it's creating a triangle. But those vectors would definitely be on the plane. And notice I have more that I could find, like I could go from A to C or from C to A. It is interesting to note, and I just want to kind of put this in the notes, that if I had went from B to A, I would have got the same vector that I got before, except all of the numbers would have been positive. And so you could say, well, yeah, that's a different one. But what's different about it is just pointing exactly the opposite directions. Like, let's point in that direction instead of this direction, but they're still kind of the same line. You understand that? So they're aiming a different direction. So, the question is BA different than AB? Well, yeah, no. So I could have went and got AC as well. I just didn't choose to do it. Now, here's where we're going to take advantage of something that we did in the last class. Do you remember what happens when you take the cross product of a couple of vectors? What does that produce? What did that do? I'm going to erase this, but if we had this vector here, U, and we had this vector here, V, and we went and decided, let's go U cross V. What did that do? Remember, it had to do with torque and the fact that vector V is not perpendicular to vector U. And we said that force and distance have to be perpendicular. And so conceptually, what that produced for us was vector v over here. So it was like the perpendicular component. So I'll call that v perpendicular, so to speak. Does it make sense that that produced vector v perpendicular to vector u? Well, I'm going to use that fact. That's what cross products produces, perpendicular vectors. Do you remember the right-hand rule and how the answer that we got for rotation was basically the length of this vector, which was perpendicular to the other two? A cross product was actually a cool trick to find something perpendicular. So if I take these two vectors as a mnemonic device, as a cool trick, if I find a b vector crossed with cb vector, this will find a perpendicular vector. Now, what I don't care is how long is it. I don't care how long it is. I just want it to be perpendicular. Remember, what are we trying to do here? We're trying to find a perpendicular vector. Well, this is a cool way to do it. So I take these two vectors sitting in a plane. I'm going to find their cross product. Now I'd like to draw that just so that you're taking a little bit of time to kind of visualize this. So
Hey Doug, out of curiosity, if you switched AB to BA, would you have to switch CB to BC to make this still work, or would it work no matter what?
No, doesn't make any difference. Any two vectors, doesn't matter if they're touching tail to tail, you know, like the one I erased, they were touching tail to tail. Nope, they can be facing off in any weird directions. It makes no difference whatsoever.
Gotcha.
That's
Just
actually
the one
why I
from the
did.
plane.
That's actually why I did CB and not BC. So that's a great question. So if I was to remember, these two vectors don't even have a location. So I'm going to draw them from 0. So if I go 3 in the x direction, notice I got to go backwards to do this. So this is my x, and this is my y, and this is my z. And since I got to go backwards, I'm going to draw a dotted line over here. And I've also got to go backwards in y. I'm going to draw a dotted line over here. This, of course, will be a lot easier to conceptualize in 3D. And I got to go backwards, you know, in GeoGebra. I got to go backwards in z. So I'm just going to graph the point -3, -1, -2. So -3 is back this way, 1, 2, 3 in x. And then it's backwards 1 in y. So I sort of made it to here, kind of to right there. But then I've got to go down 2 in z. And notice this example is going to be kind of horrible because notice my vector right there is kind of like so small and hard to see, and I don't really feel too good about it. So there's vector A, B. And then vector CB was x is -5, so we kept on going. But y was actually +1, so that puts it right here. And then it's down 1 from there. So this is even worse. So it's kind of like right there. So in a sense, the orientation in which I drew this is just not very helpful. So when we can spin this in 3D, we'll be kind of much happier. So there's CB, red, there's AB. But I'll attempt to draw this in 3D, but can you picture then that if I cross product those, let's see, I don't know, does that look okay? So 90 degrees to that and 90 degrees to that. So now that I've drawn all that in, it's, you know, utterly confusing. So AB crossed with CB is really going to be perpendicular to both of those. So in a sense, the orientation in which this is spinning is not very helpful. That's kind of the idea here. Well, let's go see if we can do it. Again, I just want to give you time to think about that. So a cross product is going to be a big part of this section because we're always needing to, as I said, find something perpendicular. So if you want to find something perpendicular, then having two vectors in a plane that you can cross product is going to find something perpendicular for you. So cross product is one of the tools we built in the previous section. So what is the cross product of those two vectors? Well, we said it looks like this. If you put I, J, and K, and it actually doesn't matter which one is which here in this case. It does if you're finding the moment, but in terms of cross product, it doesn't matter which one of these I put next. So because I wrote AB, and that's the next one, I'm going to write it that way, but I would have got the same answer if I mixed these up. So we say, let's take the determinant of that. And so in the interest of space, I'm just going to write this as a vector. So if I cross out this, and then you go -1 times -1, which is 1, minus a -2, don't you get 3? So there's my x component of my vector. X is 3. Then I come back and do the same thing again, except for I'm crossing out this row. So I go -3 times -1, which is 3 minus, notice that's actually a 10. So 3 minus 10 is -7. What's wrong with what I just wrote? 3 minus
You need the
10.
negative.
Yeah, remember how the J row, you changed the sign? So yes, 3 minus 10 is -7, but the J, you actually changed the sign, which in our case is good because we don't like negative numbers. And then lastly, you cross out the K row to get K, and you go 3 times -1 is -3 minus 6, -3, I'm sorry, 5, -3. Notice how easy it is to screw up the signs when these are all negative. -3 minus 5 is -8, and I don't change the sign of that, -8. Now, if I try to draw that in my sort of non-three-dimensional picture, I think I'm going to get kind of confused by that. But let's go draw all three of those in GeoGebra really quick, just to get you to see how significant this is. And we'll come back and, make some use of this. So I just want to be able to spin this beauty. So I can do this kind of any way I want. So I had vector A, B, but rather than label it A, B, I'm just going to go kind of cut to the quick and do this a little faster. So if I just call this vector U, and it was -3, -1, -2. And vector V, which was -5, 1, -1. So first of all, let's take a second look at that. So there's our two vectors. And I'm sort of disappointed that it didn't naturally throw labels on them. Let's see if I turn it the way. Notice this is kind of backwards from what I just drew because remember the red is actually the X and the green is the Y. The question is, if I draw this last vector, the question is, will it actually look perpendicular? 3, 7, -8. again, I'm not so much showing you this because like you don't believe me. I'm really just trying to give you time to soak in that what this is actually done and make sure that we didn't make a mistake. We being me, of course. This is where I really need the labels because I don't know about you, but I'm sort of lost now. I can't remember which one's which. I think the longer one is the kind of the U one. So is there a place I can put this that allows you to see those as perpendicular? I'd say it's right there. So do you agree that that W vector, the long one right there, is really perpendicular to the other two? Do you see the, I don't know, the genius of this process, this crazy process that we're going through to make this happen? Now, we're done. If you understand what you just accomplished. Why is that so cool? Why is that amazing that we just found that?
Are those the components of your plane?
That's exactly right. Like there, that's the equation of my plane, 3x plus 7y minus 8z. But the question is, what is it equal to? Is it 0? Remember, it doesn't have to be 0, because if we change that to something other than 0, that's just going to move it, but it's going to still stay perpendicular. How am I going to find out what that is equal to?
Does it? Well, like you're saying, it shouldn't matter, right? Can it be 0?
Not, it does matter a little bit. If you change that from something other than 0, it's going to move it around. Can it be anywhere? If you set it equal to 0, does it make sense that the point 0, 0, 0 is one of the points that's on it? Does that make sense?
Yeah.
But what was the original question? It actually had to go through, well, actually all 3 of those points. In other words, when I plug those in, do I get 0? If I plug in 2, 3, and 6 for X, Y, and Z, will I get 0? Maybe not, but whatever I do get, that's what better be on the other side. Does that make sense? Now, how do I know which one to pick? Because if I pick 2, 3, 6, I'll get one answer, but if I pick -1, 2, 4, I'll get another answer. And if I pick 4, 1, 5, I'll get even another answer.
If they're all on the same plane, you should get the same answer for all of them.
If this is correct, I should get the same answer for all of them, which doesn't seem possible, does it? If I haven't screwed up, it shouldn't matter. Isn't that what happened for a line? Like if you found the slope of the line and it was 2/3 and you went, cool, I know the equation of line, it's y equals 2/3 x plus something. And then you go back to plug one of the points in, which one do you pick? And you said, well, it doesn't matter which one. They're both supposed to work. Well, they should all 3 work here. So 2, 3, 6. So if I put in x is 2, y is 3, z is 6, what do I get? Six and 21 is 20. I really doubt I'm going to get this right. 27 and then -48. So isn't that -21? Is that true? Double check because I don't want to make this lesson lost on you. -48. Yep. But what if I stuck in one of the other points? -1, 2, 4. In that case, you get -3 plus 14 minus 32. Oh my gosh, you get -21 again. Our evil plan seems to be working. What if I plug in the last point, 4, 1, 5? I get 12 plus 7 minus 40. Oh my gosh, I get negative 21. So what did that do? It just moved the graph up. In other words, it figured out the orientation. This is, if you will, the correct slope or orientation. The reason I kind of don't want to use the word slope is you can appreciate, you know, if a plane has a slope, if I'm sort of skiing on it, then I would think, watch this carefully. If I was skiing on this slope, would you say that's a steep slope? And I would say, well, it depends what direction you're going. What if you went across this way? I don't know if you can see this. That's a terrible color. Let's use this pen. What if I skied across this way? Is it steep then? The answer is no, it's level. Like you're walking across the hill. Now, if you go down this way, you would see it slope. But it's a little hard to talk about slope when it's a plane. That's why I'm saying orientation. So all I need you to do is feel the conundrum a little bit. But the point is we got the orientation correct. We got the slope correct thanks to the 3, 7, negative 8. And then we just had to kind of slide it up or down into position. Notice in this case, it was negative 21. So we kind of had to slide it down into position. And then it was like, bam, it lined up with all 3 of those points now. Isn't that kind of cool? So we just found the equation that has the correct slope and the right location so that it actually goes through all 3 of those points. How's your brain? Is it hurting or is it happy right now?
It's feeling good.
My only concern about this is, doesn't this feel just like, I mean, in a sense, you're feeling what a Math 60 student feels when a teacher does this to them. If the teacher comes into class and say, okay, class, today we're going to find the equation of this line. And all you got to do is step 1, go y minus y over x minus x. There's your slope. And you throw that slope in right there. You know, and they're thinking, what do you mean right there? Well, you know, y is by itself on one side, x is on the other. Okay, I can memorize that. And then you come back and you throw in, you say, okay, great, that's equal to something. And then you come back and you throw in, well, pick one of those points. When y is 6 and x is 3, this has to be a true statement. So you solve that equation, you find out b is equal to 9, and then you come back and you go y equals negative x plus 9. And you're like, bam, I got that right. Can you appreciate how ridiculously foreign that feels to a student? Like the teacher teaches that and the good memorizing student can produce it. And the teacher's up front going, good job. Can you feel the student's sense the first time they've heard that of like, okay, I guess so. Like you told me I did a good job, but I don't understand what I just did. And I had to practice for like 2 days to be able to pull off that weird routine. And now you're telling me it's correct. But okay, I mean, if I don't graph this, if I don't actually go to the trouble to graph that and see that it actually does go through these points, that's a really weird process. That's a crazy multi-step process. But do you see this is no different? Isn't that weird? Like we went to the trouble, step 1, to find a couple of vectors using our 2 points, using our 3 points. And once we did that, then we cross product those, which is a crazy process itself. And then once we found the cross product, we said, okay, great, 3, 7, negative 8, there's part of the equation of our plane. And then we plugged a point in and then we found out what it was equal to. That's quite a crazy process. But the reason that feels so crazy is because those are kind of, well, mnemonic devices. It's a recognition that you can do something to figure the slope out. We can do something to find the slope out. Hey, look, we can do this. Well, what did we do? We did something even weirder to find the slope. All right. Let's see if you can pull this off then. By the way, and I'm sort of tempted to do this, but Every time I say I'm tempted to do something, I always end up doing it. I wonder if I'll be that way again. Let's go back here and consider, like, what if you had found vector AC instead? AC, let's see, AC, that'd be C minus A, so that'd be 4 minus 2, 1 minus 3, and 5 minus 6. Agree that's AC. What do you think will happen if I take the cross product of those two? Let's see, let's go CBAC. In other words, I go CB cross product with AC. What do you think is going to happen?
Shouldn't you get an equivalent vector?
Seems kind of like we should get something equivalent, right? -5, 1, -1.
Maybe some of the signs will be flipped.
2, 2, -2, -1. I love the conjectures you're making. Should be the same. Somebody saying that I didn't look up. It might have been Raymond. Maybe the signs would be flipped. Let me ask you a question. Can you mess with this equation up here and yet have the same equation? Take a look at this equation right here. We think this is the answer, right? And by the way, we didn't graph it. I should go graph that plane and graph the 3 points and see if it actually goes through them. I'd encourage you to do that, but I guess I'm not going to. Can you mess with that equation yet have the exact same equation? Is this okay? Is that the same equation?
Yeah.
That was basically Raymond's idea. It's the same equation. What about this? Is that the same equation?
Yep.
Those are the same exact equation. Like, I can do algebra to this. All 3 of those planes are the same exact plane. There's actually no guarantee we're going to get the same answer here. But we're going to get, maybe we'll get this instead. Maybe we'll get -3, -7, and +8. Or maybe we'll get 6, 14, and -16. If we were lucky, then we'd get 3, 7, -8 again. But we're not going to necessarily get the same answer. But if we get 6, 14, and -16, then when we plug our point in, we're going to get -42, and it's going to turn out to be the same equation anyway. So I kind of hope we don't get the same answer, but we're going to get what a mathematician would call a scalar multiplier of 3, 7, -8. This was a scalar multiplier of -1. This was a scalar multiplier of +2. X is a terrible thing to use in this context because it looks like cross product. But we multiplied by -1, we multiplied by 2. So let's see if that happens. Just to kind of check our work. Well, let's see if I can do this. I'm going to do this in my head and try to do it really fast. So -1 minus 2. -1 minus 2 would be -3. Notice we didn't get 3, we got -3. It makes me think this is the one we're going to get now. So I'm glad it was actually different. Let's see if we get -7 for the next one. So then I would get 5 times -1, which is 5, minus a -2. 5 minus a -2 is 7. But remember, we changed the sign of that 7 because of the middle term. And then the last one, when I do K, it'd be 10 minus 2, which is 8, +8. So had I done this one, I would have said, okay, this is the equation. And I would have said equals what? I don't know yet. Well, let's go see what it's equal to. Let's plug in one of our points. Let's plug in 415 and plug it in C. 415. So I get -12 minus 7 plus 40. That's -19 plus 40, which is +21. Same exact equation, but it's been multiplied by -1. Do you see that? So it's like it didn't matter what 2 vectors I picked. So your equation might not look the same as your neighbor's equation, if you will, but if you were to multiply it by something, both sides by something, you should get it to look the same. All right, that's kind of fun. Let's try another example. Find, let's see, is this the right time for this problem? I'm going to switch to something else. Find the equation of a plane. When you, again, when you see that terminology, you should immediately think, I'm going to have to find a perpendicular vector to whatever description the person's about to give me. So find the equation of a plane through the point 3, 4, 6. Notice I'm making this up as I go. I think it's important that I do that rather than have canned problems that come out nice, or like maybe we'll get a bunch of fractions or something through this. And so fine. Find the equation through a point, but I want it also to be perpendicular and perpendicular to a line. Remember what the equation of a line is. The equation of a line is like 2 plus 3t, 4 minus 2t, 5 plus t. That's the equation of a line. It's one way to write it. Yeah, we're definitely gonna have to spend some more time on this tomorrow. I want to do more examples with you. This is kind of a neat topic and I want it to sink in deeply, and it's already 9:15. So we'll be able to finish this example, but I have like 5 things I wanted to do. So whatever, we'll figure the schedule out later.
Sounds good.
So it goes through this point, 3, 4, 6, but it's perpendicular to some line. Through a point perpendicular to some line. Can you visualize that at all? Like what? I'm not even gonna like draw the XYZ graph. I'm just gonna say, okay, here's a point, and it's supposed to be perpendicular to this line. What does that plane even look like? It's through the point, but perpendicular to that line. Can you visualize that? Well, I guess if I kind of cruised over here to hit it perpendicular to that, that little segment is perpendicular to the line and through the point. Again, you have to see this 3D, which isn't that easy to do. And so it's kind of like that plane. The only thing that would help here a little bit, which is what GeoGebra does, is to try to come back and say, I would see this part of the line, and then it would drop behind the view, and then it would pop back out the other side. So that plane is standing up vertically. Again, I don't even know if that helps. It's so hard to visualize this stuff. How am I going to do that? So last time I gave you 3 points and said, find the equation of the plane. This time I'm giving you, can you see that there's only one? Can you see that if I find some point and I say, I want it to go through that point, but then it also has to be perpendicular to the plane. Can you, perpendicular to the line, does it make sense? I can't swing that plane any other orientation. It's got to kind of stay perpendicular to that. Well, what you should find yourself thinking is there 2 vectors? Is there 2 vectors that I could take the cross product of? Or what am I after? What do I need every single time? I need a vector perpendicular to the plane that I'm interested in, right? Do I have a vector? Do I have a vector perpendicular to my plane? Back here, the answer was no. So I went and made one. The answer this time is, well, yes, you actually do. You have one right now. You already have one. Do you see that?
Is it 3, -2, 1?
Think about Alyssa's question or her hypothesis. She said, is it 3, -2, 1? You might think like, where in the world did she get that? Because she's actually right.
Just all of the t's.
Yeah. Isn't the meaning of this line right here, from what we looked at earlier, isn't this the point 245? And then the direction of that was plus t times 3, -2, 1. So this was the location of the line that anchored it someplace in space. It goes through that point, and then it headed off in this direction, right? Well, isn't that direction perpendicular to our plane already? It's already perpendicular to our plane. Huh. I don't have to work that hard then. There it is. I have one. So you're saying the equation is 3x minus 2y plus z equals something? Yeah. How do I get the something? Remember, what this does is make sure the plane is oriented correctly. We'll go graph this after we do this and then we'll be done. How do I find the equal sign? Because we already know we got the orientation correct. It's perpendicular. So basically what I'm saying is we don't have this. You agree with that? We have that. We have the plane oriented perpendicular to that line now. Do you agree with that? But can you picture it sliding along the line? Like, how do I know where to put it now? Well, I'm putting it in such a place that it's going through that point. What does it mean to go through that point? It means that point better work. What's the coordinates of that point? 3, 4, 6. That's the only point I know here, by the way. Last time I had 3 choices. This time I have 1. It's got to go through that point. So if I go plug that point in, when x is 3, y has got to be 4, and z has got to be 6. That's going to tell me the answer to that. So I got 9 minus 8, which is 1 plus 6. This is equal to 7. So there, I think, is the answer to my problem. I think that's the answer. So let's go kind of graph all that and spin it around and have the satisfaction that we actually accomplished something here. And then we'll pick it up there tomorrow. So let me take a quick picture. Go to GeoGebra. Because this actually should feel like magic to you still. A little bit, like I'm not really feeling this. You're actually feeling, as I mentioned, what a Algebra 1 student feels the first time somebody helps them or tells them how to find the equation of a line. They kind of almost don't believe it. So we said this goes through the point 3, 4, 6. So I'm going to graph the point 3, 4, 6 to make sure it actually goes through that. I say capital A so that it doesn't think that's a vector. That's cool. Then we had the equation of the line, and we said that we could say that in a cool way. And we noticed a minute ago that the equation of our line, although we wrote it parametric, it didn't sort of like that. So I say 2 plus 3t. I think it still seems like an easier way to graph it, even though it doesn't want to do it. So 2 plus 3 times t is my kind of how I find my x coordinate. And we said our y was 4 minus 2t, 4 minus 2t. And we said our x was 5 plus t. And I think I have too many parentheses. Is it kind of like that? I don't know. So I'm gonna, oh, that was a huge mistake. And I get to do that again. 2 plus 3t. I've found this is really cumbersome. It just seems really unfriendly sometimes in terms of how it wants you to write things. And if you do what I just did, you'd think, oh yeah, there's one extra parenthesis there. I'll just delete that. And all of a sudden it deletes everything. So kind of annoying. 5 plus t. It's not as intuitive as Desmos is. So I'm supposed to be perpendicular to that line and going through that point. Can you picture where this plane better end up? It's supposed to go through A and be perpendicular to that line. And then we said, we thought the answer was 3x minus 2y plus z equals 7. So I go down here and do exactly that. 3x minus 2y plus z equals 7. And we're on the edge of our seat hoping that that meets the requirement. So notice it does appear to go through A, and it really does appear to be perpendicular to the line. So perhaps you didn't visualize this very well before, but notice the way they wrote the line here is kind of a better way to write it, in the sense that you can see that the line is emanating from 2, 4, 5, but the important thing is it's heading in the direction of 3, negative 2, 1. So that the vector for that black line is 3, 2, negative 2, 1. Well, if we want to be perpendicular to that, that's exactly what we were hunting for, is a vector perpendicular to our blue plane. Well, hey, we were actually given that in this problem, 3, negative 2, 1. Cool. I'm almost done then. It's super easy. That's cool. So it worked, oddly enough. So I'm just going to try to spin this in some orientation that I can. Unfortunately, because I made this up randomly, the point is really close to the line. It sort of would have been nice if the point was a little further away from the line. There isn't anything that you don't know actually for today's assignment. It's just that you're going to be given a number of creative types of questions, and whether or not you could, make the connection, kind of be able to do all of the problems right now. I just think you need more time to soak in this so that you can agree that, okay, this is actually easy. I got the hang of this now. So that's why I want to do a few more questions tomorrow. Maybe we'll have, time to just do part of tomorrow on that, and we can kind of start jumping into the next section. But if we fall a day behind, that's all right. We'll figure it out later. I just would rather teach you things that you deeply understand rather than kind of rush through and say we covered everything. I just think that's a good I don't think that's a good practice. So yeah, it really does look perpendicular. Cool. And it really does pass through. Anything else for the good of the cause today?
So there's no test this week. It's next week.
Yeah, we're going to put 13 and 14 together. So there's only one test at the end of next week. Last day class is Thursday. That's the plan for the test. So we, need to look at a little bit of chapter 14. Of course, they go together. I didn't just throw them together because I thought we were out of time. We're going to be looking at let's see, what was the name of that topic? Vector valued functions. And basically that's what this is right here. That line is a vector valued function. That line is defined by a vector as a starting point, and it's defined by a vector in the direction in which it goes. And so that is a vector valued function. That's what 14.1 is. And so they go together.
And is this kind of where Math 254 picks up from?
Yeah, that's exactly correct. 254 picks up, and in one sense, this class starts out being about infinite series and whether they converge. And notice we're kind of doing something that's sort of unrelated. It's almost like you could make the concept of an infinite series like a 4-week class, and then you're done. And then this last part of 253 is really that would mean vector calc is more like a 16-week class. So in a sense, we're kind of starting on Calc 4 right now. But even if you don't go on to Calc 4, whatever reason, you don't need it, etc., don't have time. Just the fact that you're at least introduced to the concept of equations in 3 dimensions is kind of cool. It's kind of neat to be asked to take that jump mentally, conceptually into this world, even if you don't kind of go deeper and find equations that are much more interesting. Because notice we just found the most boring equation in 3D that exists. It's a flat plane. That's the most boring equation you can get. But we want equations, that are like mountains, and we want to climb on them and figure slopes out. And that's kind of what you do in Calc 4. As I said before, if you have any way that you can take Calc 4 this summer, just because it's neat to see, it's really a cool landscape. All right, I've held you too long. Get out of here.
I was actually wondering if you had any more information on the commencement that the college is having. I know that they're supposed to have us like drive a route on Redwood campus, but they haven't sent out like any more guidelines with a map or anything, as far as I know.
That's too bad, because it turns out that I volunteered to organize that and I made the map.
Oh, okay.
So
Well, I'll check in with my classmates to see if they've gotten anything.
the gist of it is you're coming in, I think it's called the east entrance. You're coming in on the side that students typically come on where you park. You're coming in that side, and then usually you wrap all the way around to the parking lot. You're sort of taking your first right, which is kind of a wrong way on a one-way street, if I remember right, from the east entrance, and then you're just kind of wrapping through from there.
Okay. Okay, yeah, I'll look it up on the campus map and find out if anyone else has heard anything, but yeah.
Yeah, I mean, I can actually show you, but I'm a little more concerned about the.
Yeah, it's no problem. I can wait. I just
Larger.
wondered, if they were going to send it out at some point. So
I'll send an email to some of the leadership people and ask them to post that or something, because it seems like something you should know the answer to. I guess what are we? No, we're not that far away. It's only 2 weeks now, isn't it?
yeah, I think this week and then next week is the last week.
Yeah, it's right after that. I'll send an email.
Okay, thank you.
Yeah, have a good day.
You too.